to take a ball, any kind of ball or a cylinder, and roll it off like a curved platform like this, you can pretty much guess what it's going to do. It's going to go that way. But I want to show you what happens if we take something that's much lighter, so air is going to have a significant effect, and do the same thing. This is just a little piece of notebook paper, and it's just wrapped into a cylinder, and the ends are fastened with tape. And watch closely as I roll it down the ramp. Watch what it does. Ready? What did it do? Went backwards, right? It's nothing to do with any breeze. Here, watch, I'll do it in another direction. Always comes back this way. You see, when you see something like that, it makes me wonder why so many people, for so long, thought that the curveball was an optical illusion. Since all you need to do is to take something that's somewhat more influenced by air friction relative to gravity, and you can demonstrate it pretty easily.
All right, the pitcher's mound in Major League Baseball is 60 feet, 6 inches away from home plate.
Great. You take this and say when to stop. How much further?
Keep going.
How about now?
I'll let you know.
Are you saying stop and we're just too far away to hear you?
Okay, stop.
Are you kidding me?
That's 60 feet.
There's no way this is 60 feet.
I'm looking at it.
You realize this isn't one of those times I want you to exaggerate?
Okay, so anyway, what I was getting at finally was that it's 60 feet from the pitcher's mound to where the batter is. So that's a number we want to keep in mind. I'm going to come back to that. And it's a roughly 400 feet if you went, right to center field to get a home run. So let's take a little bit of a look at this now. I actually did a little computation. You can put some equations together, use quadratic drag and stuff like that. And what I did was I considered what would happen if the batter hit the ball at, go away. Yeah. The batter hit the ball at 110 miles an hour and at a 35-degree angle, which is actually optimal in the air. And if you were in Philadelphia, it would land about right here. May or may not have a home run, depending on, exactly where the ball went left and right. But if you were in Denver, and this is to show you the importance of drag, the importance of air friction. We all know what gravity is doing. Ball goes up, gravity pulls it down. That's the easy one. But the drag force due to the air is much more significant than you might think. Because if you were in Denver, if it weren't a home run in Philadelphia, it probably would be at 5,280 feet, which would be your altitude in Denver, where the air is a lot thinner. And in fact, if we were to take the air out of the picture altogether, it would go beyond 700 feet. So you can see the important nature of drag. You see they start out the same here. But the drag plays a significant role on the ball, and in the absence of air, you can go over 700 feet. Now, where might you go to be able to play baseball or some kind of athletic event where there's no air? The moon, right? So we could go to the moon. On the moon, if you did the same thing, 110 miles an hour, 35 degrees, that's the trajectory it would follow. Now, by the way, there's an important distinction that needs to be made here between mass and weight. The bat may weigh only 1/6 on the moon of what it weighs on Earth, but it has the same mass, so it will have exactly the same effect. It will be just as hard to get it swinging, and I see the physicists in the audience among whom I know are nodding yes, like this, right? Well, what about the moon? You see, you can easily tell that there's no air on the moon if, in fact, you watch dust. You see, when they kick up dust on the moon, it follows a ballistic trajectory. It follows the same path that a brick would, because there's no air. So let's take a look at what would happen if, in fact, we kicked up some dust on the moon. Okay, and could somebody push a button for me up there? I lost my control here. Is there going to be any end to technical problems? There should be a play button, you know, if you bring the cursor down to the lower left. Well, I'm not even seeing my thing anymore here. Disappeared. Can you move a cursor there manually on the machine? Do you have cursor control up there? You see, we could go to the moon, but we can't get a stupid laptop computer to work right. Yeah, except where's the button? Go back and let's see if it's there. Can't have disappeared. Can you go back one? Oh, I got control again. I've got control again. Unless you're doing it and it just looks like I'm doing it. All right, I got it. Okay.
Hard rock, but it's covered with vines and tailors. And we have to see to the bottom. I think we'll get a chance to look further down. There you go.
So forget about him falling. That really wasn't interesting at all. But you could see the dust go up and down and follow a ballistic trajectory. And now, you know, another one here is where he's trying to put a core sampler in, and it goes in. Okay, this is really funny.
Hey, John, while you're sampling there, you might look around and see if you see any particular result. That's what I'm looking for. Good job. I told him you were. Okay. We see that one went all the way in. Not quite.
So you can see the trajectory of the dust, right? Yeah. Oh, by the way, golf. Do you realize a golf ball has been hit on the moon by none other than Alan Shepard? He had to do it with one hand. Those suits are kind of cumbersome, but let's take a look and see what happened here. Miles and miles and miles. Well, not quite miles and miles, but really, really quite a distance. In fact, if I expand the scale a little bit, here we are back in Philadelphia with our 110 mile an hour ball at 35 degrees. And let's imagine that we built a stadium on the moon. We built a stadium on the moon, and let's suppose we pressurize it to about half of atmospheric pressure and see what kind of event we might be able to have. That's how far it would go. Same angle, same speed. So, do you realize the kind of athletic events that you could have on the moon? Can you imagine how much money we could make from this and us poor scientists could go along for the ride? I believe that this nation should commit itself, before this decade is out, of placing a stadium on the moon. Okay, Well, what about the trajectory and the necessary reaction time? The trajectory and the reaction time. The person catching the ball has to be really well aware of where he is, watching the ball at all times, making sure that he's keeping his eye on the ball. Well, sometimes it works, sometimes it doesn't. But when it works, it's pretty amazing. So, throwing the ball. Let's take a look at the pitch first, okay? The pitch is going to come in at a very high velocity.
Yep. That was a close one.
Okay.
Too late for him to cancel?
I think so.
That's up! Watch out!
Well, a pitch thrown at 90 miles an hour, and that's not the fastest that's been done, it's been over 100, will cross home plate in about half a second. Now, it takes almost 2/10 of a second between the time the batter starts to move and the time the bat crosses the plate. And it's almost 2/10 of a second reaction time from when the ball is thrown to when he figures out what to do. Now, if you start adding that up, you realize that the ball hasn't really gone very far from the pitcher's mound before he has to start to swing and get lined up. Just to show you how fast this really is, and even to add another dimension to it, take a look at this video here. I had a hard time finding really good videos that show what the ball is doing. But this is a good one. Let's take a look. So not only is the ball going at lightning speed, you can see it's not even going in a straight line. And you can imagine how much that complicates what the batter has to do. Well, that's the thing. You see, it looks like it's coming right at you. Nobody, I believe, who really isn't an extraordinary player or a professional would actually be able to stand there without jumping out of the way. And once again, I do seem to have lost control. So, thank you. Mouse person in the background. Okay, good, thank you. And I got it again. Here's the explanation for that curve. And I put the word curve in, curveball in quotation marks because, strictly speaking, some things that are called curves are
as the
not
ball's
really
moving
curves.
forward through the air, if it's spinning, the air is flowing around the ball from the front to the back. The ball is spinning in the same direction as the airflow at the top of the ball, but in the opposite direction at the bottom.
So the ball is
Because of
going that
friction
way.
between the air and the ball surface, air is dragged around the top of the ball downwards towards the back, but at the bottom of the ball, the airflow and the ball are opposite directions. The air comes to a screeching halt fairly soon, instead of being deflected upwards. The net result is air is deflected downwards. Due to Newton's third law, the air exerts an equal opposite force on the ball, which is upwards.
So, how would sports players take it?
So the ball is exerting a downward force on the air. By Newton's third law, the air is exerting an upward force on the ball. This doesn't necessarily mean up or down. It could be left or right. Depends on how the ball is spinning. And to just give you an example of that, imagine that and this is called the Magnus Effect. Imagine that the ball is thrown to your left and it's spinning in a counterclockwise direction, which is the opposite of the one we just saw in the video. The net result is that there's going to be a downward force, at least a downward force on the screen. So the ball will follow a trajectory that looks like the red line there instead of the straight green dashed line. Now, I tried to throw a curveball, but not with a regular ball, but one of these track balls. You see, now I'm not very good at it, but what I did was I let it spin off the end of my fingers that created a direction which is going to be the opposite one than compared to the one in the next picture. So watch this in slow motion. You can see a clear, clear change in path off to the right. Now, here is my neighbor, who's somewhat more athletic than I am, who was able to throw a curveball by having it spin in the opposite direction. Which would be something you can achieve even as an amateur, but is much harder with a baseball. Now, here, using the little trackball device where I can really speed it along, watch how pronounced the trajectory, the curve of the trajectory is. Right. Now, that's no optical illusion, right? Not even close. And then I wanted to explore what happens if, in fact, we have one ball thrown right-handed and the other thrown either backhanded or left-handed, so that we have opposite spins. And watch what happens. You see how they go off in opposite directions, even though they were thrown toward the same point, amazingly enough. And here it is with the balls moving away from it. And finally, something we spent most of Easter trying to achieve is having the balls actually cross paths and then come back in the opposite direction. And that's not what I wanted. One moment. See that? Going back in the opposite direction. There's someone saying, wow, because that's like, 7 hours later, Let me skip this for now. I want to give some special thanks to a number of people. But before I close, I do have, I want to show you what our Easter was like here. And with that, I'd like to thank you for your attention.